Good afternoon, everyone. Good afternoon, everyone. Thank you for coming, everyone. My name is Paul Check. I'm the chair of the Department of Chemistry and Biochemistry here at Providence College. It's my great pleasure to welcome you to the inaugural Anna E. Lavoie Memorial Lecture. My faculty colleagues and I are very pleased to host this very special event. This gathering demonstrates just the ambition and accomplishments of just two of our many excellent students who've done the science programs at Providence College over the years. Annually, we'll be inviting a prominent person in the sciences to give a lecture about their work and bring everyone together to show what people do with science degrees in society. The teaching and scholarship at Providence College has been strong for decades, and the future looks even brighter. We're very excited about the construction of a new $50 million science complex just next door to where we are right now. And the challenge has been difficult at times, but it's a monumental commitment by the college. Father Shanley and the Board of Trustees have made a commitment to keeping the sciences strong at Providence College. It might seem a little countercultural to have a science lecture in a building dedicated to the humanities, but of course things are not always as they seem. People who train in science know that where you start isn't necessarily where you end. Science is not so much about the content of what you're studying. When we're training our students, it's about the process of asking and having questions answered. Problems in the world abound, and what could be more humane than finding a path to curing a disease, feeding the world, engineering a solution to something what might seem as simple or basic as providing safe water and sanitation in a remote part of the world. That's why events like today are critical to communicate to the wider world on campus and beyond. We're streaming now live all over the world. I can say that, can't I? Teresa and Eddie are wonderful examples of what happens when a talented student uses a Providence College science education as a foundation for a life of meaning. They've achieved a great deal already, and as you will learn shortly, they're full of initiative, creativity, and skills that will enable them to accomplish much more. These alums should inspire our students, many of whom I see here today, and make us proud to be part of this Providence College academic community. It's now my pleasure to introduce Father Shanley, our college president. Father Shanley's leading PC through a period of unprecedented growth and change. Examples are all around us. We're so pleased he's here today to share a few thoughts and introduce our featured speaker. Please give a warm welcome to the 12th president of Providence College, Father Brian J. Shanley.
Thank you, Paul, and welcome. It's a real pleasure for me to see so many people here. We have standing room only, it seems, and that's always a nice problem to have, and we'll figure out some seats back there before this lecture gets going. As Paul mentioned, this is the second time I've been in the Ruane Center introducing people who esteemed graduates of Providence College. About 2 weeks ago, we had Dr. Bob Gallo, who discovered the HIV virus here as part of a panel. And today we welcome back two of our best as well. And it's a testimony to the quality of our programs here at Providence College and to the faculty here present. I know that as a faculty member myself, there's nothing more gratifying than seeing your students flourish in the way that our two speakers today have. So you guys in the chemistry department are really doing something right to produce graduates like this, and I hope this is a day of joy for you as well. And as Dr. Check mentioned, you never know. I try to ratchet people's anxieties down all the time about the connection between a major and what you do with the rest of your life. There's very little connection. I was a history major and I run a college. How is that helping me run the college? But I would say that the main goal of education is learning how to learn for your whole life. And I think both of our graduates here today show that lifelong love of learning that has led them down different paths than perhaps they thought when they were undergraduates here. And it's exciting for all of us to see the myriad possibilities that come out of majoring in the sciences at Providence College. I want to thank Teresa especially today. It's her generosity that has made this inaugural lecture and the series to follow possible. And it's a wonderful tribute to her mom as well, and she'll talk about that later on. Today is Giving Day at PC. We've never had one before, and our goal was to get at least 1,917 donations today and raise $100,000. And the good news is we've beaten both goals, as far as I know right now. And really, the stuff that Paul is talking about, the things we've been able to do here, have been born out of philanthropy. All of the changes that have occurred here have occurred as a result of the generosity of people helping us make Providence College an even greater institution. So Teresa, I want to thank you personally and publicly for this, and thank all of you who might have given today. I also want to mention that both of our graduates here were also members of the Liberal Arts Honors Program, of which I'm also a graduate as well. And I think there's a connection between the path their lives have taken, not just with chemistry, but also with the robust liberal arts education that they received in the honors program. And we always boast about how no matter what you study at Providence College, you do get a good grounding in the liberal arts that rounds you off in a way that doesn't happen at a lot of other schools. And I think the honors faculty ought to be equally as proud as the chemistry faculty, well, maybe not quite as proud as the chemistry faculty about our students coming back here today. It's my privilege to introduce Eddie, who, as I said, was a member of the Liberal Arts Honors Program. After excelling at Providence College, Eddie went on to the Ivy League to earn a master's degree and a PhD in molecular biophysics and biochemistry at Yale University. After graduation, Eddie earned a highly coveted Kauffman Fellowship, where he studied healthcare entrepreneurship. And today, Eddie is utilizing that liberal arts education by combining his science background with an entrepreneur's ingenuity and spirit in the emerging field of digital medicine. In case you don't know what that is, he's going to explain that in the lecture. He co-founded Achille Interactive Labs in Boston, which focuses on digital medicine, and also serves as vice president at PureTech Health, a biotech company where he helped launch their digital medicine sector. A leader in his field, Eddie recently appeared on CNN with Sanjay Gupta to discuss his pioneering company, so he's a celebrity. His work is changing the way scientists think about medicine and medical treatments, and that's what he's going to explain to us today. And we are proud to have this PC alumnus at the forefront of the cutting edge of digital medicine. So please join me in welcoming Dr. Eddie Martucci. Eddie?
How's that? Good. All right, we'll clip. Well, thank you, everyone. This is a great turnout. I'm really honored to be here. Thank you to Teresa and the whole Lavoie family. This is a type of event that I certainly didn't have the experience of having. I guess no one did, since this is the inaugural. So there's one checkbox for me within the obvious sector. But this, I think, philosophically is really important, which is that Father Shanley stole my thunder. So I was going to say something along the lines of the fact that being a scientist or a certain type of training, to me, actually has nothing to do with what the end career is. It's really about a way of thinking, a way of approaching the world, and a way of solving problems. And I feel, I say often, actually, that what I got at Providence College scientifically was a strong foundation, and psychologically, I guess, and also scientifically from the non-science department, was an openness to new ideas and a collaborative, discussive atmosphere all the time. And the more that I think we can embrace that, the better. And so what I'm going to hope to tell you is how that same type of thinking is changing the medical field a bit. So again, thank you, Teresa and the family. I talk a lot. So there's a lot of people here that can attest to that, probably way too much. I probably talked in class a lot. I've got some family. So I've got 30 to 35 minutes, which I can almost guarantee you I'm not going to hit because I really like what I'm talking about, but I'm going to try. So what's happening today is something pretty amazing. I feel fortunate to live around and actually work in a field where we're seeing dramatic changes that I believe we've never seen at this pace before. So medicine historically, you'll see the graphic representation of this at the end. Medicine historically has been very narrow, and there's a good reason for that. Medicine's important for us. It's important for some of the most serious problems that humans deal with. It also always has safety implications. And so when we think of medicine, as a society, we've been really protective in terms of what we consider medicine, even what the definitions of medicine are. So much so that actually medicine today comes to me, and if we said, go take your medicine, most people are thinking, putting a pill in their mouth. And that's okay. Pills have been amazing for us. Drugs, pharmacology have transformed our society. But the world of medicine has been really hesitant or resistant to break out of that boundary. And again, like I said, there's good reasons for that. But what I believe we're seeing in the last not even a decade is a dramatic change, not only in the type of medical products coming out, but actually the philosophy of medicine, of how we approach what we call as a society medicine and what we accept as true medical practice. And I think it's actually getting back to the original intent of medicine, which some folks can remind us had nothing to do with the modality, but had to do with caring for patients. So what I'm going to hopefully bring you through are a number of examples, some of which I'll spend a lot of time on my own company and our work, but a number of examples where new technology is actually accelerating at such a pace, and new thinkers are doing things in a way that we're trying to take new technology and make it impactful and break down a lot of these types of barriers of medicine. So that was the title of the talk. But what I'm hoping by the end that I can convince you, and that we all as a society can get to in the next 5 or 10 years, is that instead of a phrase like this, can that be medicine, which hopefully everyone reads, there's a little bit of incredulous tone in there, right? A little bit of disbelief, is that it changes just to something that we call unexpected medicine. There's no tone in that. There's no judgment. It's really medicine. We just didn't expect it before. And so let's, I guess, get going on that. So my background, obviously here at Providence, trained in biochemistry and biophysics. The work I did, I was always very interested in human health and in pharmacology, and so worked on a couple research programs that had to do with small molecule-based pharmacology. Worked on a couple other things as well, got some good research training. I went directly to Yale, as Father Shanley mentioned, and I spent about 5 years kind of dually in the MB&B program, which is a really classically trained structural biology and biochemistry program. Has a couple Nobel laureates, a recent one in that department. But I spent half my time in there and half my time in the pharmacology department, training under Karen Anderson that does HIV and anti-parasite work. And so I moved from smallish molecules to smallish molecules inside really big molecules, proteins. And then I changed pretty dramatically from there. So I spent, 9 years straight almost thinking about molecules and molecular interactions, but more broadly thinking about science. And through that process, I got a bug of, entrepreneurship, startups. I was really fascinated by it. And I was fortunate enough to join a group called PureTech Health, which today it's actually a London-based UK public company, but it's founded and based here in Boston, well, here on the Northeast in Boston. And the whole mission of PureTech is to take science that is very high quality, that is new and groundbreaking and could be impactful, and bring it there by forming companies around it and trying to develop new types of medical products out of that type of science. So the science that might be languishing, or the science that might be really interesting and make a quick splash on a CNN article, and all of us say, wow, that's really fascinating, and we never do anything about it, to instead do something about it. So I was fortunate enough to go here. And my whole job for about a year or two was literally just reading science, talking to scientists, and thinking about how we could make those companies. And so I got a kind of interesting immersion in what we might call like protected entrepreneurship. I'm really careful to say I'm not the type of entrepreneur that went out and staked every last dime he had on building a company. I was working in a job that allowed me to do entrepreneurship in a cozy way. And I formed a handful of companies there. I was on the co-founding team of a company, 3 or 4 companies, one of which is very interesting in the human microbiome space, the good and bad bacteria in and around us. That's up in Boston right now. But what I got really interested in was the brain. And myself and a small team at PureTech were fascinated. About 6 years ago, there the way that the industry viewed the brain was actually at a kind of low point in history. There had been a few decades of drug research that had solved some major problems, both actually through treatment, but also philosophically in terms of, for instance, treating mental health disorders. But there was a lull. And the problem was across neuroscience, almost no one was going after the brain anymore. So 6 or so years back, almost every major pharmaceutical company was either totally shuttering their neuroscience programs or was significantly paring them back and changing their focus a bit. And so much less was going into this. But that came at the same time that the problems were actually getting worse, and we'll talk about a few of those. But it didn't seem like there was a viable path through traditional medicine. Also at the same time, if we can believe this, it's within a decade that we've had phones in our pockets, right? And so we got really fascinated by this sort of dualism, which you could never say, you would never think should exist, where we have medicine in the brain and then we have technologies over here and consumer grade technologies, and they should really never intersect. That's kind of that old view of protected medicine. But it turns out if you think about what these technologies are, they're data harnessing machines, right? Apple, Google, and others do better than almost anyone else in the world at making these things extremely precise data capture instruments. They're also specifically designed to embed sensory input in a way that's powerful because they want people to use them. So we got really excited by the idea that what if you could take these technologies and use the best of what we know about the brain and engineer technologies that could actually not just sit around the brain when you're on your couch, but actually impact the brain in a meaningful way through either treatment or diagnosis. And the reason we thought that we could do this, by the way, this is a real brain. One of my scientific co-founders, Adam Ghazali at University of California, San Francisco, this is actually his brain functioning, a map of his brain, which he did through fMRI, with his brain functioning as he just sits and looks at a screen. And what's kind of amazing about this is that we understand what we've actually understood for many decades, which is that the brain is a set of receptors, but targeting receptors through small molecules, which is what we generally think of as neurological drugs, is only half the story. The rest of the story, and maybe more than half, is actually what, I'll go back and do it again, is actually what's happening in a millisecond by millisecond basis as the brain coordinates electrical signals and coordinated networks to different parts to be able to do things like speak. We knew this, but we didn't know how to harness it. A set of neurological findings over the last about 10 years convinced some of my colleagues that we actually could harness it for the first time. And it was this perfect storm of new technology that can actually stimulate your brain like this, but not predictably. New neuroscience that says, no, 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 if we can actually target you right there, and I'm just fake pointing, but if we could target you right there, we can actually change something about your brain in a predictable way and hopefully create a new type of medicine. And so we formed a company called Akili Interactive, it's my company, with this mission statement that we kind of coined, and since we're a business, we also trademarked it, which is generally a good thing to do, and super cheap, by the way, if you ever really want to do it. A couple $100 and you get like 2.5 years to hopefully use it somewhere. So imagine what medicine can be. Medicine is really the operative word there. It's the important part. And our take on this was that we could take this type of device, an iPad, and by coding in specific algorithms, marry that with the very best, most high compliance type of technology you've ever seen, which is video games. When people play video games, they really play video games. People love video games, and actually almost all people, just different types of video games. And so this was our idea, even before we had a technology. Before we had a specific neuroscience underpinning to it, we said, we're pretty confident that we can go out and find the neuroscience. Again, my whole team that I worked with at the time were all scientists by training. We said, we're pretty sure we can go find the neuroscience that needs to be embedded into this and make this real, because we had seen a lot of findings that were sort of taking the next step in understanding the brain. And if we could, then we could create a field that actually looks like this. That now, as I said, after decades where you progress to the point where medicine means pill, we could actually progress, in some ways you might almost say backwards, but backwards by going forwards, where medicine means a lot of things. Medicine allows you to have new technology that can sit alongside or even alternative to drugs in some cases. So this is what we went after. And what drove us to go really full bore into medicine, as I mentioned, drug industry was pulling out of neuroscience. The very best thing that we think sensory stimulation and these new technologies and like video games could attack is what's called cognition. So how the brain functions and operates and processes information and thinks. And it turns out, and we still firmly believe this, not everyone is there, but we still firmly believe that cognition is actually the unmet medical need of the next decade. And why? So when we think about how do we build a business, we do actually have to build something that hopefully will make money someday. There are major, major patient needs. And so on top of making money, we want to help a lot of people. So ADHD, there's a good chance that there's like, I don't know, 10 or 15 people in this room that have ADHD. Luckily, with most of the things I'll show you, the stigma has gone way down. There's a standard of care for ADHD, and it's Ritalin. But there's about 30% of ADHD patients that walk out of a doctor's office and don't take medication. They just do not want medication. There's another 15 or 20% that take medication and it's not working for them. And so they're trying month to month to take new drugs, and they're really not happy with the fact that they're drugging themselves to get to this endpoint. So big need there. Depression. I think most people understand that this is still a massive need in our society, that we have 8 million or more Americans, and then overseas just as many. It's not a country-specific thing. But most people don't know that in depression, only 50% of patients actually respond to the first drug therapy. And about 25% of patients are refractory to 4 different therapies, drug therapies. So again, a whole half of the pie there of patients that could use a different approach if it could work for them. Multiple sclerosis, this is a different one where we don't actually think of autoimmune disorders generally as having, being related to like fast-paced neurological function. It turns out as an industry in healthcare, we've done a really good job addressing multiple sclerosis. We now attack the autoimmunity pretty strongly by a number of drugs. There's a few multi-billion-dollar drugs out there that are treating the condition very well. After successful treatment of multiple sclerosis, the number one long-term predictor of quality of life is cognitive function. The number one long-term predictor of return to job status is cognitive function. And none of the multiple sclerosis drugs actually target cognition. So you have 50%, 30 to 50% of multiple sclerosis patients that now don't have pain anymore. They can walk. They're not actually having demyelinization anymore in their brain, but now they're at a lower cognitive functional state, and it's significantly impacting their life. And then finally, the biggest problem we have across the world, really, over the next 20 years is Alzheimer's, and that's a big blue circle, because as we know, there are no disease-modifying agents for Alzheimer's. Doesn't mean that there won't be, but there's a huge gap there. So we went out and found, looked across the world really, talked to hundreds of neuroscientists, and found a technology that to us was really exciting. And I think there's a number of technologies like this now. This was at the time by far the best. But a technology that was out of UCSF. Eventually, it published as the cover story on Nature, in the Nature journal, which is probably the preeminent biomedical journal, next to things like JAMA and New England Journal of Medicine. And this technology was a very rudimentary, very simplistic, we saw kind of fundamentals of what a game could be. And what it did was it algorithmically challenged a person to do a fine motor task at the same time that they're reacting to things in their environment. And the underlying theory there is that the weakest part of cognitive function for humans generally, not any specific type of humans, but just humans generally, is processing multiple types of information with competing goals. And so what this technology did was in a very specific way, there's patents filed on it that we've licensed. We've filed a number of patents on it as well. Teresa's firm is actually helping, but there's no conflict of interest there, just totally randomly. The technology in a very specific way layers on different tasks, different sort of conflicting information that the brain has to keep up and process real time in a way that's pretty powerful. And so the results, do not try to read this whole thing, but just to highlight a few. The brain up there that has a circle with a little red dot in it, this was a placebo-controlled trial. That circle, red dot on the brain, I guess I have a pointer maybe. No, whatever. There we go. That guy. that is actually the group that's using this technology after a month. These were healthy 60 to 80-year-olds that came into this trial, went home, used this technology for a month, and came back and had their brains imaged and looked at through EEG, electrical signals. And this was actually after a month of doing it, it actually substantially changed their brain. So now when they process information, when something is shown to them in their view, they extremely highly activate. Red in this case is activation. It's a really bad figure because it's totally counterintuitive. But they significantly activate the midline prefrontal cortex, which is the center of the brain that controls goal-directed behavior and what we call cognitive control. Interestingly, it also connects that activation to other areas of the brain in a really robust way, such that older adults here, eventually, if you look at that, start to look like younger adults in how their brain is actually connecting different regions when they see stimulus. And then finally, everyone drops off over time in being able to process multiple streams of information. But if you take and train roughly average age 70-year-olds on a technology like this for a single month, and then retest them at the end of that month, they're actually processing, compared to these placebo groups, they're actually processing sensory stimulus better than a 20-year-old at baseline. So this was really interesting to us, but it still doesn't tell us a whole lot about medicine, except that this lab had also run a small pilot study with the same technology looking at clinical measures. No one will know what these names are necessarily. The one I want to focus you on is C up there. TOVA is the test of variables of attention. This is an outcome measure that actually the drug industry uses for assessing attention and impulsivity in ADHD trials. And so what you see here, blue is this technology group, the multitasking intervention group. Significantly outperforms placebo, actually 300% or more improvement. And you don't have to worry about what that millisecond variable is. But it's big. It's real improvement in a measure that actually maps to a clinical condition. Now, these people did not have ADHD. They were also on average 70 years old. So it takes a pretty massive leap of faith to see that figure and then say, let's put this into children with ADHD and see if it works. But that's why we're in startups. And we said, let's try to do that. And so we went full bore into creating what we call digital medicine. There's a few other companies that around the same time in different non-brain areas started using the same phrase. So there's a burgeoning industry of what we call digital medicine. We were pretty distinct in that whenever most companies, especially startups that don't have a lot of money, try to run away from the FDA, we went and sat down and knocked on FDA's door and talked to them and said, we want you to consider this, if it works, real medicine, and approve it. And after multiple discussions and collaboration, FDA said, sure, but it's got to work. So they worked with us to design trials. So the type of product that we're hoping to bring to market is something like this, right? A medicine you've never quite seen before. This is a child actually using a version of our game. I'll show you in a minute. I should say our medical device, because we're a medical device company. We have a set of PhDs and neuroscientists and clinical trial folks that are with me in Boston. And then the other half of our company is north of the Golden Gate Bridge in San Francisco, and they all come from the game design background, Electronic Arts. My first hire was, I ripped him out of LucasArts before they got bought by Disney. He was the executive art director of the entire Star Wars franchise of films and media. And so we try to put a polish on this that feels like consumer-grade software, but we think it can fit into a traditional medicine paradigm. We don't think there's any reason why you can't think about this like medicine. So it can be doctor-prescribed. Right? It's going to be FDA approved as long as it works. We've talked to insurers, and there's at least some insurers that are going to seriously consider and probably reimburse this. It can be in a monthly subscription model, which in medicine, a monthly copay, monthly prescription from your doctor. So it doesn't have to feel sort of from an infrastructure perspective and how medicine and healthcare are deployed, it doesn't have to feel much different. But of course, it can have a ton of different benefits and things that have never been done before in medicine. So very clearly, you have a very different reaction and interaction with the patient than you have in the drug industry. And by the way, I'll show you in a second, we're not against drugs. I keep positioning us as different from pills. We actually collaborate with the pharmaceutical industry pretty extensively. And what they like is that you get this type of response. Instead of go take your medicine, you have a patient who actually not only will engage in their medicine, or not only will take their medicine, they'll engage in it, they'll love it. And we think we can develop a new type of relationship that the traditional medical world is actually having a problem with which is sort of a trust-based relationship with the patient. And so what we're very excited about in my commercial team, I'm not a commercial guy, so the commercial team I hired is really excited about is there's a whole set of business models that revolve around having trust and interaction with a patient, which is something that our current medical system actually lacks pretty significantly today. So quick video. This is actually a snapshot of our product that is in trials currently in pediatric ADHD to give you a sense of medicine.
This interstellar transporter will take you to the far reaches of space and time. As the Evo Explorer, you will collect new, exciting specimens throughout the universe. Keep it up! You've got this! Here are your targets. Tap OK.
So I don't know if you can hear me. I'll try to talk over it. So this looks and feels very familiar. It feels like what kids are used to playing. Every aspect of the sensory environment that you're looking at here is specifically designed and encoded to activate a certain part of the brain. And then we look at that and test that over time. But it, of course, has the enjoyment, it has the engagement. People feel accomplished.
Keep it up!
We have a custom soundtrack, which is what you're hearing right now that we wrote. Awards.
Almost there!
And so imagine a kid going into a doctor's office and being given this. So it's exciting. We can make a trailer, right? We can make something that's really sexy and cool, and that's all that shows. All that shows is we can make a really awesome trailer. But of course, our whole business is clinical trials and clinical data because we're a medical company. So we've run a number of trials across different patient populations. This is data from our first, what we call our phase 2 trial in ADHD, children with ADHD, 8 to 12 years old. Very briefly, only focus on the top. This was done at Duke University and a number of other centers. On this measurement, this objective attention performance measurement, the average child without ADHD scores at about a -1. That's the orange line that goes across. The average ADHD child in that age range starts pre-intervention, pre-treatment at about a -6. On average, we can take ADHD kids from a -6 to over halfway toward a typical child. More important than that, 33%, not everyone's a great responder, but 33% actually end up at the end of that trial above the orange line. So they're indistinguishable from an ADHD child, at least on this outcome measurement. And then you can see some of the stats here that are pretty interesting and exciting to us. We conveyed nothing about whether this was working for the child. We didn't tell them anything, really. It's a blinded trial. Over 3/4 of parents reported that the time spent was worthwhile, and almost all of that, 77%, wanted access to it after the trial. We had 0 adverse events, 0 safety issues, which should be obvious from a video game. In this population, you usually get 10 to 15% safety and dropout issues in trials. So it's very different. This is just a phase 2 trial. We're actually going forward before we bring this to market. We're, of course, not selling it yet. We're going stepwise, just like a drug company would, through multiple phases of clinical trials. So right now, today, we're over halfway done in a large, it's about 12, it's 12 sites now nationwide, phase 3 trial sanctioned by the FDA, the first ever large-scale randomized double-blind controlled trial with a video game, which is pretty cool. And so hopefully those results will read out by the end of this year, and we'll rapidly, if they're positive, go to FDA and get approval, at which point we would be approved as the first medical product that operates like a video game. And we think it's important. But what we built was more than a single product. We didn't want to build a single product company. There's risk reasons for that. We wanted to sort of spread the shots on goal. That's like the biggest phrase in startups. But we also felt like we didn't know where our technology was going to be best and most powerful. So early on in the first year of founding the company, my strategy was just to get different aspects of our technology, different parts of our platform, and build products across a number of neurological conditions to see where it's best. So ADHD is our furthest along program in terms of development and closest to market. But you can see we have a number of programs that actually go far beyond that in areas that you might not expect. And I mentioned partnerships. So we partner with lots of academic and clinical centers, but we do partner with pharma. And if you can imagine me, before we had this, before Sanjay Gupta interviewed us, 5 years ago when some people still didn't even have iPhones or Androids, believe it or not, and sitting in a pharmaceutical company and telling them, you should really invest in video games. The conversation didn't go that great. We were kind of laughed at. So just like anyone in startups, you have to have a thick skin. And so one of the biggest things that me and my whole team are proud of is that we now count Pfizer as a partner in Alzheimer's, which I'm about to tell you about, and 3 major pharmaceutical companies that are actually direct investors in my company, meaning that they own equity. So they're not just interested, they're not just partnering, they're actually owning part of our company, a very small part, but they're owning part of our company because they believe in it and to share in the upside of a brand new type of medicine. And so what gets me excited and what we get so proud about is we really hope our products work, but we also think that us and a number of other companies are changing pharmaceutical companies' minds, changing really the world's minds, doctors' minds about how you can treat conditions. So that's treatment. I'm going to totally shift gears and talk about Alzheimer's. I would be remiss if I told you that big blue circle, which is the biggest unmet need in the world, and then not talk about Alzheimer's. So Alzheimer's disease is a major problem, no disease-modifying treatments. A bigger problem, which is not spoken about much, is that we actually don't even have a really good way to find patients in the future. So I actually just flew back from London yesterday. I was at what's called the World Neuroscience Innovation Forum on a panel there, and the entire panel and what turned out to be the entire conference was about how, in God's name, do we find early patients, early Alzheimer's patients. And the reason is really important to everyone in the industry. It's because we know a few things today in Alzheimer's. We can generally get high-risk people, but not very well. Family history, early subjective memory complaints, but it is not a very good predictor of who might develop Alzheimer's. We can really predict it if we can do PET or CSF. I don't know, does anyone know what PET is? Positron emission tomography, CSF, cerebrospinal fluid. So the 2 ways that we can really know if someone's developing pathology and plaques in the brain, in one case you have to take a radioactive tracer and sit in a PET imaging machine while they image your brain. And by the way, you have to be near a center to do that, and they have to ship the tracer within 24 hours because it decays, because it's radioactive. Or, and that's the good option, because the other option is you have to have a lumbar puncture to take out cerebrospinal fluid and see if there's amyloid in there. So the huge problem, there are drugs that are trying to target these amyloid plaques across the industry. Every major pharmaceutical company has a program here in phase 2 or phase 3. The big problem is if we get a successful drug prescription, we have this major white gap in the middle. Because, and I've heard pharmaceutical companies mention this to me directly. They mentioned it publicly yesterday at the panel I was on. Even if we have a successful drug, even if we finally have a way to treat Alzheimer's, there's no way to actually get to patients in the real world. Because you have literally millions of people that are age 65 to 70, and if you want to treat them before there are overt symptoms, you're not going to PET scan or spinal tap millions of people in the country. It just logistically doesn't work, and no one's going to go for it, and insurance is not going to pay for it. So we actually started a few years ago a collaboration with Pfizer that they fully funded, and it was a collaboration that tried to use our digital technology platform in a very different way, which is to think about filling that gap. And hopefully everyone's mind's already going there. That like, well, maybe digital technology, it's scalable, it can be downloaded by people. It's not scary, right? Compared to a spinal tap, it's really not scary. And so we ran a trial, and these data were presented by Pfizer, actually, at the world's largest Alzheimer's conference last December. I will go ahead and admit to everyone here, I did not think this would work. This is a little bit crazy. We have to reproduce it, but we're excited, and the industry's excited. So what you're looking at here is a single, it's less than 20 minutes, about a 16-minute test, just using one of our game products with these algorithms. So sitting with an iPad for less than 20 minutes. And what we did in a blinded fashion was look at people that are all healthy, entirely healthy, roughly on average age 70 years old, 74 actually, people that had amyloid plaques in their brain, the hallmark of Alzheimer's, and people that did not. These people are entirely healthy. A doctor cannot tell you which one of those have amyloid in the brain. The only way you know is by doing a PET scan, which was done in the study on every single person that came in and was screened. And what we found is kind of exciting. So for people who aren't used to looking at scatter plots every day, these are my favorite type of graphs to look at. I like putting it up, and then you can just get a sense of the data. If it's not very clear, if you draw a line at about 7.5, okay, a horizontal line at about 7.5 on our proprietary score, and you look below that line, that's a performance line. Imagine 15 minutes, draw that line, you get a score, look below it, about 90% of those dots. Small sample study, we don't go out and say this absolutely works, but if these data are reproduced, about 90% of people below a threshold value from a 16-minute test, we could tell you very likely have amyloid in their brain. So instead of scanning the entire population, which logistically can't be done, but even if it could, you're going to get a 10% hit rate. You can imagine that technologies like ours and others could scan everybody, because it could be a downloaded link. It could be something that they pick up in their CVS and do a 15-minute test. And now, instead of a 10% chance, we say, well, look, we have maybe a 90% chance that you're actually starting to develop the early signs of Alzheimer's. Now insurance is going to pay for that. Now you can actually funnel people into a neurologist and get the care they need. So this is something that we were also not the first company to think about this use case. There are really cool companies, a company using the camera on the iPhone to try to image the same amyloid, but in the eye, because they believe there's trace amounts that actually come through the blood-brain barrier of these amyloid plaques, and actually the monomers end up circulating in the eye. So there's a company developing that. There's a company called NeuroTrack, which is using your TV to flash different pictures at you. Because it turns out that before you have overt memory symptoms, you actually have covert memory symptoms, which is that when you're shown something new or old, a normal person who does not have these issues will dwell on the new picture, because our brains like to forage new information. Someone who doesn't yet have overt memory symptoms but is starting to develop Alzheimer's will actually dwell on those equally. Very quick eye saccade movements that you can use from like a little Logitech camera on your TV. So there are a lot of companies now that are going after this, and it's really exciting because it shows you not only the power of digital technology, but also the scale of it. And so I hope to see more work there in the future, and this is what we hope we can do. We can take something that is actually not possible and disconnected and maybe create a clinical workflow that now allows you to get to millions of people that could use care. This is, of course, heavily dependent on the pharmaceutical industry getting drugs that work. I've seen some of the data. I fundamentally believe that we will get there in Alzheimer's, and so we're going to need tools like this. So whether it's us or whether it's one of these other companies I mentioned, I really hope someone fills in that yellow box soon. So that's what we do. There's a lot on what we do, actually, instead of a little bit. And that whole set of medicine was actually related to building specific products, and the other companies I mentioned as well, purpose-built products like our product, where they were based on science, but they said, in order to get the type of data we want, yes, we can use the iPad, but we're actually going to fundamentally build new software from the ground up to harness data in the way we want. But there's a whole new set of technology, not at Akili, but some folks I know and some folks I don't know in the medical industry that are actually looking to go even a step beyond that, which would be what's called low burden or passive sensing. And so this is something that in the past would have looked like something from the Jetsons. I don't know if everyone knows what the Jetsons is. I hope so. I don't know, give me another cartoon from like 12 years ago. So where a human is standing in their living room, and there's connected devices all around them that are monitoring their physiology. This is actually attainable. Huge companies like Sony have actually said they want to have a tablet in every single room of the house of the future that is actually interacting with the patient, both in entertainment ways, but also in physiological ways to measure physiology. And maybe in the future, doctors can even then, if they notice a problem, tighter up or down something about that digital environment and treat them. So it sounds crazy. It sounds like science fiction, but so did FDA-approved video games 6 years ago. So I think we can get there. And my favorite example, my favorite scientific example of this has to do with sound and ambient environment. So this is a free downloadable tool. It's not very easy to see. It's actually measuring my voice. I'm not sure if you can tell that. So if I say like, PC, 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 right? That's how Alexa works. That's how Siri works, right? There's a very specific signature, the triple PC right in the middle, that is measuring my voice. Of course, everybody's a little bit different, so it has to start to understand what you say. This is pretty cool. at the Consumer Electronics Showcase this year, the #1 biggest area of consumer entertainment technology that they highlighted was actually voice recognition and voice tracking. It's why Alexa is like one of the fastest growing products in the home. It's why Siri sometimes annoyingly goes off when you say something by mistake that sounds like Siri when your phone's sitting on the table. And by the way, what Amazon and Google and Apple can do is probably 1,000 times better than this. This is a free downloadable tool. But the question is, can we harness that for health? Can we do something good with that? And the early indications are yes, and this is super cool. So the same type of pretty simplistic voice tracking, this was an experiment that was first published out of MIT, these two researchers here, Cummins and Epps, out of the Lincoln Lab at MIT. It was actually a defense-funded lab that's connected to MIT, showing that a very simple and short stretch of sound of spoken voice looks different when you look at a healthy speaker versus someone who has clinical depression. Hopefully you guys can see the variability there. This is actually common across physiology, discussion for another time, but we tend to think of variable physiology as a negative thing, but it's actually not true. So physiology that's variable and samples a wider dynamic range, for instance, this top graph, actually usually tends to correlate with a healthy status. It probably gives us some flexibility in our physiology. You can see that that variability, the total dynamic range is depressed in a depressed patient. Didn't mean to make that pun. And so this could be exciting. If you take this to the next step, there's a technology that's now being developed in Boston by a company I'll mention in a second that is using spoken voice from a single 30-second sound sample. For instance, asking, you're standing once a day, you're standing in your living room and it says, "Hey Eddie, how's the weather?" Alexa to me, and I go, "Okay," and I just talk for 30 seconds quickly as I'm putting my clothes on. A single 30-second sample was run in this study on people who had depression and who didn't in a blinded trial. I'm not sure if people are used to looking at, these are called ROC curves, ROC, response operator curves. They're diagnostic curves. You want this line, if you're going to be a diagnostic, a clinical diagnostic, you want this to be super sharp and super high. And these 0s to 1s are actually, think about that like a %. So what this is telling us, and you can trust me on this if you don't know how to read these curves, what this is telling us is that from a single 30-second voice sample in this population with roughly 90% sensitivity and specificity, or said another way, about 10% false positive rate, pretty good, you can tell if someone has depression from a single 30-second sound sample. I have never seen, I've been looking at mental health for the last roughly 10 years in my job, I've never seen a physiological measurement, blood draw, anything like that, a traditional diagnostic that even comes close to this. I've never seen a neurological measurement, like a brain scan, that even comes close to this. So this is pretty exciting, and this company is called Sond Health. Again, I'm not involved with them other than that we're buddies. But their tagline is, "Your health speaks, and we listen." And I think that's a really interesting example of where a massive problem that we can't attack with traditional medicine is being attacked not only with new technology, but with technology that's already going to be sitting in everyone's home, and you could even co-opt. You could even passively just turn it on. Tons of Big Brother issues with that, tons of data safety and patient privacy issues with that, but let's forget about the negative for a little while and focus on the positive. And so finally, what if we can go with new technology where traditional medicine not just is not performing well, but where it literally cannot go? And this is actually my favorite example of a technology over the last 5 years that I've seen. Even more interesting to me than our own technology. This is, of course, a picture of a newborn on its mother's chest. And there's a problem with newborns and especially premature babies in medicine today, which is that we cannot develop new traditional medicine, meaning pill or injectable technologies for them, because these babies are too fragile. And so whether it's clinical trial sites not wanting to experiment on the smallest little life form that we tend to have today, whether it's the FDA, and I've seen this a couple times with companies, tell companies that you cannot do experimental medicine even when it's really, really promising in animal models because that baby is so tiny. There's a problem. The problem is, rather, you can't do it. The companies shut down, technologies languish because they're not allowed to experiment on little babies like this. if you can leverage a physiological contact here, most people recognize this as skin to skin, which is a paradigm that everyone pretty much endorses. And it seems to work to actually calm the baby's physiology, but not for the reason that is common knowledge and that you think. So skin-to-skin contact for humans generally, not even a baby and a mother, releases oxytocin, right? So everyone's probably read stories. It's sort of a hormone release. It's the hug hormone. It's the happy hormone. That's absolutely true. But there's something else going on here with this little baby, which is that for the last, let's say it's a preemie at 7.5 months. For the last 7.5 months, there's been one constant for this baby every second, roughly, of the last 7 months, which is the mother's heartbeat. And babies don't hear, babies feel. And so this baby has been perceiving its mother's heartbeat through bone conductance, actually, in the womb for the last 7.5 months. This baby is now born before it was supposed to be born, probably, evolutionarily, has lost that. In actual mice, the biggest stress paradigm of mice is actually called maternal separation. So this baby, like all babies, has been separated from its mother, but it's a very fragile baby right now. And so one set of researchers, actually up in Boston as well, out of Brigham and Women's Hospital, had postulated that maybe it's the heartbeat that's actually going on here. And how can we leverage a heartbeat? How can we test that? They did a lot of experiments, and it turns out it's absolutely true. The heartbeat is actually doing this. If you have a baby and a mother actually go chest to chest, the baby's heart rate after a while will actually normalize to a mother's. Not exactly, because babies can't come as low as a healthy adult woman, but they will normalize. They'll actually synchronize some of those EKG patterns together. It's pretty amazing, but then again, this baby's been living for 7.5 months in that environment. So this set of researchers, his name's Amir Lahav, thought, what if we could do that for babies that actually can't hang out with their mom because they're in incubators? And so don't look at the bottom, that's the surprise one. So the top one is brain structures. So this is looking at a couple different brain areas that are generally thought to imply good brain development, and I'm not going to go deep into it. And what they did was they built a little system where they piped in a real human heartbeat into the base of an incubator at Brigham and Women's Hospital and a couple other hospitals. And what they found is fascinating, right? Statistically significant. The auditory cortex at negative days of life, right? That's how we think about these babies. They're not even supposed to be here. At negative days of life, you can start helping them develop their auditory cortex in a way that's meaningful. That's important because even preemie babies that actually end up not having massive shock problems are massively predisposed to developmental delays, et cetera. A drop in other brain structures is actually a good thing, and so it's interesting that the brain changes. But to me, the most interesting set of data, which is blurry here, is actually related to heart rate. So if you pipe in as an intervention, as a therapeutic to a baby, within seconds of piping in a maternal heartbeat into an incubator, the baby's heart rate drops. And the kind of crazy thing, and there's a lot of different studies that have shown this now over the last 2 years, that minus this one, it's hard to see, there's one baby in here that actually doesn't, it works for almost every single baby. That their heart rate comes down when maternal heartbeat goes pumping, and almost within a second or two. The crazier thing, and I don't have a good graph for this, I was trying to find it at the last second. The crazier thing is that you get about double this effect if you put the baby's own mother's heartbeat in the incubator versus a different woman's heartbeat. So there's like kind of a natural evolutionary connection to the mom's heartbeat that's really powerful. And so my question and the inventor's question here, well, he's certainly asking the question, I'm putting it out there, is could you harness that for a therapeutic potential? A baby that maybe is about to go into total decompensation and total shock, which happens a lot, and those babies have about a 50% chance of living. Can you actually use that heartbeat to, the mom's heartbeat, to in some way rescue the baby, to in some way pull down their physiological reactive system and prevent something like that? These data don't show that at all. These data just show there's a kind of smallish drop in heart rate. But it's not crazy to make the leap and say, well, if you can acutely get a smallish drop in heart rate, at the beginning of a shock episode, can you actually pull back and rein in that physiology so that we can intervene without flooding the baby with chemicals? I don't know. No one knows the answer to that. But hopefully in everything I've told you and what we're now starting to accept in medicine, why don't we try, right, for this guy? Why don't we use digital technology in a way that drugs cannot do or traditional medicine can't simply because it's too hard to experiment on it? This guy ran a trial with these things in multiple incubators in a hospital because it's safe. It doesn't even touch the baby. And so what I would say, and hopefully what a lot of people are now asking, is why not in medicine? If the data's there, if the science is there, why don't we do things? Because we should try. The worst you can do is fail and show that it doesn't work. The worst you can do is spend a little bit of money, but it's absolutely worth it. And so here's where we are in medicine today, I fundamentally believe. That's my super exciting PowerPoint graphic for you guys. Do you want to see it again? Here, ready? So medicine before, now it's blue, and now it's wide. But I actually think this is happening today. I think that for the first time in a long time, new ideas that only have maybe a smidgen of data, but kind of convincing data, are being accepted into the bounds of how we define medicine. They're being accepted into the way that we could practice medicine and the way that we could help people. And by the way, it's really fun because you get to work with new technologies, you get to think about things in a brand new way. And so right back to the earliest point and what Father Shanley mentioned, thinking differently, thinking scientifically, don't have to be the smartest person in the world, but you can hopefully make an impact. I'm hoping my company makes an impact. We're not yet on market, but we're crossing our fingers that we get FDA approval. All the other companies I mentioned are doing the same thing. So I want to again thank Teresa and her family. I want to thank everyone here because it was really exciting for me to come, and again, a big honor. And so thank you all for your attention, and happy to take questions. Yeah. Yeah.
We have time for some questions for the audience. There's so much to talk about. All I could say right now is wow. But Eddie's happy to answer a few questions. Steve, in the back.
Well, thank you for not surprising that you know the technology has influenced everything. Question relating really to the therapeutic applications you talked about. The traditional field has often unexpected and undesirable consequences. Side effects, we might call them. In fact, some lead to addictions. And I guess when I think about the game as possible therapy,
Yeah.
I wonder about unexpected, undesirable consequences, including addiction. In fact, that probably, I guess we already have to acknowledge that there is an addiction.
Yeah, so I would be, it's a great question. I would be the biggest hypocrite in the world if I touted unexpected medicine in a positive way, but didn't talk about the unexpected effects of digital technology. And there are plenty of people now writing articles and trying to research the negative effects of technology. I think it's possible, for sure. When we run our clinical trials, I talked a lot about the efficacy and the outcome measurements that we use. We actually do safety assessments in the exact same way that a drug company would. We've been, I guess, fortunate that we've had 0 safety issues, including addiction, in ADHD population. We did have side effects in a Parkinson's trial that we did, where some small percentage, but a meaningful percentage, were actually having greater motor problems, right, exacerbating their motor issues, and a little bit of nausea, actually, maybe something to do with the motion, but like somewhat severe. So I think it's an accurate question. I think when I talk about doing medicine well, when other companies in this digital medicine field talk about doing medicine well, part of that is accepting that there might be negative consequences, and so I think we have to measure those at the same time. The cool thing about technology, when you mention addiction, is we can actually solve a little bit of that. So very simple mechanic, probably the easiest things our software engineers have ever had to build, we actually lock out the player at 30 minutes a day. We can sense when they're trying to log back in too many times, and so we give a little ping to the clinical site and in the future the parents to remind them and give strategies. So when you're connected with a patient, you can do some of those things, but there will, not only should we measure them because there might be, I guarantee there will be side effects with technology that we didn't anticipate. So we have to be mindful of it and keep measuring them, again, like we would any other medicine. Dr. Cornelia?
Thank you for your talk. I was wondering, in your ADHD data, you showed a before and after, but you didn't have a control group where you'd have your game that's specifically designed to test to stimulate the areas of the brain. Could you have your gamers develop a control game that would not do that and then show the difference there?
Yes, and we have. So the first trial I showed that published in Nature with individuals 60 to 80 years old, that did have a control. And actually, when I mentioned this big phase 3 trial that we're in right now, it is the first with a technology like this that has a purpose-built placebo type or sham type control in it. So we actually sat down twice with the FDA and hashed out how in the world do you build a placebo of a video game. And it's not really a placebo, and without going through all the sort of different parts of what they call equipoise. The major difference is if I put a placebo and a drug up here, you actually physically can't tell the difference between those two. If I put a game and a placebo game, you can absolutely tell the difference between those two. So that's what we do. We purpose-built a game, something that in our phase 3 trial could have an effect, right? And that's actually what's communicated to the families. It's a word and language and educational-based game. It's actually a high bar for us. We think it might have an effect, right? A child engages in something intellectual, it actually should improve them over time. But the way that we blind it, the way that we message to the patient, lets them not really know which is the one we're testing. And in fact, the biggest way we do that is to say we think they both might work. So hopefully when we're superior, crossing our fingers, what we'll be able to say to docs, and this is why it's important, is that it wasn't just a randomized controlled trial. This is actually beating something that you might recommend anyways to your patients to do. This is like significantly better than that. So it's not easy. It took us a lot of time to come to a kind of simple-ish implementation. We also test beforehand what we call expectation of benefits. So we actually take ADHD children and their parents and put in front of them different versions of games and measure them on how they think they're likely to perform, and then we pick the one that's most closely matched. So we are doing that, and I think you have to. I think that what they call killer experiments in the digital world, there's a whole lot of people that can run really crappy trials, and a lot do, and a lot get fined now, thankfully. But the killer experiments are always where you have a control. That's when you know if you actually have something or if it's a placebo response.
Thank you for coming. My question is that how do you know the elements of everyday games you
That's a great question. I'm glad you asked it. Yeah, sure, I'll repeat that. So he asked really, really insightful question. How do you know that the skills that are improving in these patients, so let's take the ADHD kids, how do you know that the skills you're improving are improving beyond the game and aren't just improving when they're engaging in the software? So I should have done a much better job of explaining that. It's the most common question I get from our investors too, of course, and the FDA. The outcome measures I showed, where the children are improving, those are not measures that are collected in the game. Those are actually clinical measures that are collected at a clinical site before and after they do the trial, and they're kind of accepted drug measurements. We also take symptom measurements from the parents and teachers. So what we're measuring when we say something works, we actually, as a principle, and I think this is underlying your question, we specifically don't look at anything in the game because we think that would be kind of bad science. So what we're looking for is what they call transfer of benefit. Of course, everybody improves in the game. Some people improve really dramatically, but the outcomes we measure and the improvements we've seen are on standard clinical tests at clinical sites removed from when they're actually using the device. So we believe that they're real effects, and most of the sort of symptom report and parents reports are that they're having an effect. Actually, a paper is going to publish. Maybe people here can send it around April 5th, so I guess that's about a week, showing that there's also some lasting benefit on standard symptom rating scales. Same things that docs in the real world use to track if an ADHD patient's getting better or not. We see benefits up to possibly as long as 9 months after 1 month of treatment, but again, on endpoints that are not in the game.
Matucci, thank you. You started your work in small molecules. I guess I want to know if you think your
Oh my word. Thank you all for coming. This has been, it's been an incredible time. Yeah, so sensory, okay, so what we're doing, if you think about it at a deep level, is repeated and robust exposure to specific sensory stimulus that has a pretty dramatic impact on the brain, right? You can visualize that. Environmental stimuli absolutely trigger sort of what's, if folks here have taken the classes, epigenetics. And so it means you have sort of encoded genes, then you have expressed the non-expressed genes, and then you have differential expression patterns and sometimes new combinations based on environmental factors. And it doesn't just mean environmental factors that are getting into your blood and binding to genes. So I think, you know, in the brain, what we're seeing here is what a lot of people would call neuroplasticity. So the brain is actually changing, and the evidence we have is about the wiring of the brain. How is it communicating the efficiency of the wiring? How's that front part of the brain communicating to the posterior regions that process noise and sound, et cetera? But at least one theory for why that happens, why the brain rewires, is that it has to do with differential gene expression patterns. We haven't measured that, though, and it would be a pretty cool experiment. Yeah, possibly.
I'm sure that everybody in the room has a question for Eddie. Eddie, we'll have a reception upstairs in a few minutes, but just please join me in thanking Eddie for his visit.
Thank you. Thanks.
I'll call you up in a minute.
Thanks.
I really wanted to take a little bit of time and really honor our benefactor today. Dr. Teresa Lavoie has made this and the all future annual talks possible. Dr. Lavoie was a PC chemistry major who, after graduating summa cum laude, went on to earn her doctorate from Princeton and her law degree from the University of Minnesota. She's currently a law school adjunct professor at the University of Minnesota. She represents a combination of educational and practical experiences in making it work in her law practice, where her clients include biotechnology and biopharmaceutical companies. A leader in her field, Dr. Lavoie mentions young lawyers in the Twin Cities area, and she leads her firm's patent boot camp program, sharing her expertise with colleagues in an important area of practice. She's been recognized numerous times by Managing Intellectual Property, a publication, including a notice in 2016 as one of the top women in IP. Dr. Lavoie created this lectureship to honor her mother, Anna, and a means of helping our students follow in her footsteps. Please join me in welcoming her to share a few remarks.
So I'll be brief because I know we've run over a little bit. And first I want to thank Eddie again, because when I started talking about this with Steve Duria in the Office of Institutional Advancement, I think he's here somewhere, a few years ago, what I really wanted to do was something impactful, because my education here had a huge impact on my life, not just my career that I took, which I absolutely love, and I think we all saw from Eddie that he absolutely loves the career path that he took. But my friends, some of whom are here, I don't know where they are, but they're here somewhere, there they are, best friends for life that I met freshman year here at PC, and the rigorous scientific and liberal arts training, the skills in writing that I use every single day, the analytical science skills that I use every day. They work perfectly in my job, and I work with a lot of startups like Eddie's company. I don't do his work. This was a complete coincidence, actually, that my law firm does their patents. But it's just this blending of science and writing and meeting with exciting people who are really interested in their science, really trying to solve some big medical problems and unmet needs. I think it's just fascinating. And PC gave me the ability to do that. The combination of the science program that I had here and the liberal arts program, the honors program, really made me able to achieve a career path that I absolutely love. So I wanted to do something impactful. You've heard that word a number of times today, impactful. And so I wanted to set up this lecture series for the students, really, to be able to come and see these incredible people like Eddie, talk about their careers, their career paths, and see, you know, being a scientist doesn't necessarily mean being chained to a lab bench somewhere and not, you know, getting out and you're in a dungeon somewhere and it smells and it's, you know, fires are going off. It can mean starting companies. It can mean changing lives, right? It can be me going and talking to 10 different new startups that are doing drugs in all sorts of areas, traditional medicine and non-traditional medicine, or unexpected medicine, I should say. So that was one of the goals that I wanted to do, was something impactful for the students here so that they could see a wide range of what you could do with this science degree and the liberal arts degree, too. the other reason was to honor my mother, Anna Lavoie, who's a huge impact on my life. My father is here. 5 of my 6 siblings are here. My sister Suzanne, who is an MD, she lives in Virginia, she couldn't make it, but they're all here. We learned a number of incredible lessons from my mother, but hard work, an emphasis on education, and you know, an unfailing commitment to excellence in whatever you do, whether that's making a meal, cleaning the house, doing your homework, being a friend, being a sister, being a mother, excellence in everything you do, that commitment. She was the hardest working person I've ever met, still to this day, and so I wanted to honor her with this in her name. And she was a big reason I came to Providence. She was sort of the one who pushed me to apply here, and without that, I wouldn't be here, and this whole thing wouldn't be here. So thank you all for coming, and we have a reception upstairs. Students, please come, talk to Eddie, you know, talk to him about his career path that he took. You can talk to me. We're all happy to see you, and thank you again for coming.
A small token of our appreciation, we really think this is very special. Students from all 4 class years came up to me this week and were looking very forward to this event, and I'm glad they came. For students who aren't chemistry or biochemistry majors, I brought a stack of change of major forms. I'll be right upstairs, and I was also told by the organizers upstairs, this is not the normal cookies and punch after a talk. We have a very nice reception with some very nice hors d'oeuvres, so hopefully everyone will meet us upstairs in about 2 minutes. Thank you.